Chapter 2 of Science and Hypothesis. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Anna Simon. Science and Hypothesis by Henri PoincarÄ. Chapter 2. Mathematical Magnitude and Experiment. If you want to know what the mathematicians mean by a continuum, it is useless to appeal to geometry. The geometer is always seeking, more or less, to represent to himself the figures he is studying, but his representations are only instruments to him. He uses space in his geometry just as he uses chalk, and further, too much importance must not be attached to accidents which are often nothing more than the whiteness of the chalk. The pure analyst has not to dread this pitfall. He has disengaged mathematics from all extraneous elements, and he is in a position to answer our question: tell me exactly what this continuum is, about which mathematicians reason. Many analysts who reflect on their art have already done so. M. Henri, for instance, in his Introduction à la théorie des fonctions d'une variable. Let us start with the integers. Between any two consecutive sets, intercalate one or more intermediary sets, and then between these sets others again, and so on indefinitely. We thus get an unlimited number of terms, and these will be the numbers which we call fractional, rational, or commensurable. But this is not yet all. Between these terms, which, be it marked, are already infinite in number, other terms are intercalated, and these are called irrational or incommensurable. Before going any further, let me make a preliminary remark. The continuum thus conceived is no longer a collection of individuals arranged in a certain order, infinite in number, it is true, but external the one to the other. This is not the ordinary conception in which it is supposed that between the elements of the continuum exists an intimate connection making of it one whole, in which the point has no existence previous to the line, but the line does exist previous to the point. Multiplicity alone subsists, unity has disappeared. The continuum is unity in multiplicity, according to the celebrated formula. The analysts have even less reason to define their continuum as they do, since it is always on this that they reason when they are particularly proud of their rigour. It is enough to warn the reader that the real mathematical continuum is quite different from that of the physicists, and from that of the metaphysicians. It may also be said, perhaps, that mathematicians who are contented with this definition are the dupes of words, that the nature of each of these sets should be precisely indicated, that it should be explained how they are to be intercalated, and that it should be shown how it is possible to do it. This, however, would be wrong. The only property of the sets which comes into the reasoning is that of preceding or succeeding these or those other sets. This alone should therefore intervene in the definition. So we need not concern ourselves with the manner in which the sets are intercalated, and no one will doubt the possibility of the operation, if he only remembers that possible, in the language of geometers, simply means exempt from contradiction. But our definition is not yet complete, and we come back to it after this rather long digression. Definition of incommensurables. The mathematicians of the Berlin school, and Kronecker in particular, have devoted themselves to constructing this continuous scale of irrational and fractional numbers without using any other materials than the integer. The mathematical continuum from this point of view would be a pure creation of the mind, in which experiment would have no part. The idea of rational number not seeming to present to them any difficulty, they have confined their attention mainly to defining incommensurable numbers. But before reproducing their definition here, I must make an observation that will allay the astonishment which this will not fail to provoke in readers who are but little familiar with the habits of geometers. Mathematicians do not study objects, but the relations between objects. To them it is a matter of indifference if these objects are replaced by others, provided that the relations do not change. Matter does not engage their attention, they are interested by form alone. If we did not remember it, we could hardly understand that Kronecker gives the name of incommensurable number to a simple symbol, that is to say, something very different from the idea we think we ought to have of a quantity which should be measurable and almost tangible. Let us see now what is Kroneker's definition. Commensurable numbers may be divided into classes in an infinite number of ways, subject to the condition that any number whatever of the first class is greater than any number of the second. It may happen that among the numbers of the first class there is one which is smaller than all the rest. If, for instance, we arrange in the first class all the numbers greater than 2 and 2 itself, and in the second class all the numbers smaller than 2, it is clear that 2 will be the smallest of all the numbers of the first class. The number 2 may therefore be chosen as the symbol of this division. It may happen, on the contrary, that in the second class there is one which is greater than all the rest. This is what takes place, for example, if the first class comprises all the numbers greater than 2, and if, in the second, are all the numbers less than 2, and 2 itself. Here again the number 2 might be chosen as the symbol of this division. But it may equally well happen that we can find neither in the first class a number smaller than all the rest, nor in the second class a number greater than all the rest. Suppose, for instance, we place in the first class all the numbers whose squares are greater than 2, and in the second all the numbers whose squares are smaller than 2. We know that in neither of them is a number whose square is equal to 2. Evidently there will be in the first class no number which is smaller than all the rest, for however near the square of a number may be to 2, we can always find a commensurable whose square is still nearer to 2. From Kroneker's point of view, the incommensurable number 2 is nothing but the symbol of this particular method of division of commensurable numbers, and to each mode of repartition corresponds in this way a number, commensurable or not, which serves as a symbol. But to be satisfied with this would be to forget the origin of these symbols. It remains to explain how we have been led to attribute to them a kind of concrete existence, and, on the other hand, does not the difficulty begin with fractions? Should we have the notion of these numbers if we did not previously know a matter which we conceive as infinitely divisible, that is, a continuum? The physical continuum. We are next led to ask if the idea of the mathematical continuum is not simply drawn from experiment. If that be so, the rough data of experiment, which are our sensations, could be measured. We might indeed be tempted to believe that this is so, for in recent times there has been an attempt to measure them, and a law has even been formulated, known as Vechten's law, according to which sensation is proportional to the logarithm of the stimulus. But if we examine the experiments by which the endeavour has been made to establish this law, we shall be led to a diametrically opposite conclusion. It has, for instance, been observed that a weight A of 10 grams and a weight B of 11 grams produced identical sensations, that the weight B could no longer be distinguished from a weight C of 12 grams, but that the weight A was readily distinguished from the weight C. Thus the rough results of the experiments may be expressed by the following relations: A is B, B is C, A is smaller than C, which may be regarded as the formula of the physical continuum. But here is an intolerable disagreement with the law of contradiction, and the necessity of banishing this disagreement has compelled us to invent the mathematical continuum. We are therefore forced to conclude that this notion has been created entirely by the mind, but it is experiment that has provided the opportunity. We cannot believe that two quantities which are equal to a third are not equal to one another, and we are thus led to suppose that A is different from B and B from C, and that if we have not been aware of this, it is due to the imperfections of our senses. The creation of the mathematical continuum, first stage. So far it would suffice, in order to account for facts, to intercalate between A and B a small number of terms which would remain discrete. What happens now if we have recourse to some instrument to make up for the weakness of our senses? If, for example, we use a microscope, such terms as A and B, which before were indistinguishable from one another, appear now to be distinct. But between A and B, which are distinct, is intercalated another new term, D, which we can distinguish neither from A nor from B. Although we may use the most delicate methods, the rough results of our experiments will always present the characters of the physical continuum, with a contradiction which is inherent in it. We only escape from it by incessantly intercalating new terms between the terms already distinguished, and this operation must be pursued indefinitely. We might conceive that it would be possible to stop if we could imagine an instrument powerful enough to decompose the physical continuum into discrete elements, just as the telescope resolves the Milky Way into stars. But this we cannot imagine. It is always with our senses that we use our instruments, it is with the eye that we observe the image magnified by the microscope, and this image must therefore always retain the characters of visual sensation, and therefore those of the physical continuum. Nothing distinguishes a length directly observed from half that length doubled by the microscope. The whole is homogeneous to the part, and there is a fresh contradiction, or rather there would be one if the number of the terms were supposed to be finite. It is clear that the part containing less terms than the whole cannot be similar to the whole. The contradiction ceases as soon as the number of terms is regarded as infinite. There is nothing, for example, to prevent us from regarding the aggregate of integers as similar to the aggregate of even numbers, which is, however, only a part of it. In fact, to each integer corresponds another even number, which is its double. But it is not only to escape this contradiction contained in the empiric data that the mind is led to create the concept of a continuum formed of an indefinite number of terms. Here everything takes place just as in the series of the integers. We have the faculty of conceiving that a unit may be added to a collection of units. Thanks to experiment, we have had the opportunity of exercising this faculty and are conscious of it. But from this fact we feel that our power is unlimited, and that we can count indefinitely, although we have never had to count more than a finite number of objects. In the same way, as soon as we have intercalated terms between two consecutive terms of a series, we feel that this operation may be continued without limit, and that, so to speak, there is no intrinsic reason for stopping. As an abbreviation, I may give the name of a mathematical continuum of the first order to every aggregate of terms formed after the same law as the scale of commensurable numbers. If then we intercalate new sets, according to the laws of incommensurable numbers, we obtain what may be called a continuum of the second order. Second stage. We have only taken our first step. We have explained the origin of continuums of the first order. We must now see why this is not sufficient, and why the incommensurable numbers had to be invented. If we try to imagine a line, it must have the characters of the physical continuum. That is to say, our representation must have a certain breadth. Two lines will therefore appear to us under the form of two narrow bands, and if we are content with this rough image, it is clear that where two lines cross, they must have some common part. But the pure geometer makes one further effort. Without entirely renouncing the aid of his senses, he tries to imagine a line without breadth, and a point without size. This he can do only by imagining a line as the limit, towards which tends a band that is growing thinner and thinner, and the point as the limit towards which is tending an area that is growing smaller and smaller. Our two bands, however narrow they may be, will always have a common area. The smaller they are, the smaller it will be, and its limit is what the geometer calls a point. This is why it is said that the two lines which cross must have a common point, and this truth seems intuitive. But a contradiction would be implied if we conceived of lines as continuums of the first order, that is, the lines traced by the geometer should only give us points, the coordinates of which are rational numbers. The contradiction would be manifest if we were, for instance, to assert the existence of lines and circles. It is clear, in fact, that if the points whose coordinates are commensurable were alone regarded as real, the incircle of a square and the diagonal of the square would not intersect, since the coordinates of the point of intersection are incommensurable. Even then we should have only certain incommensurable numbers, and not all these numbers. But let us imagine a line divided into two half-rays, demi-droites. Each of these half-rays will appear to our minds as a band of a certain breadth. These bands will fit close together, because there must be no interval between them. The common part will appear to us to be a point which will still remain as we imagine the bands to become thinner and thinner; so that we admit as an intuitive truth that if a line be divided into two half-rays, the common frontier of these half-rays is a point. Here we recognize the conception of Kronecker, in which an incommensurable number was regarded as the common frontier of two classes of rational numbers. Such is the origin of the continuum of the second order, which is the mathematical continuum properly so called. Summary. To sum up, the mind has the faculty of creating symbols, and it is thus that it has constructed the mathematical continuum, which is only a particular system of symbols. The only limit to its power is the necessity of avoiding all contradiction, but the mind only makes use of it when experiment gives a reason for it. In the case with which we are concerned, the reason is given by the idea of the physical continuum, drawn from the rough data of the senses. But this idea leads to a series of contradictions, from each of which in turn we must be freed. In this way we are forced to imagine a more and more complicated system of symbols. That on which we shall dwell is not merely exempt from internal contradiction, it was so already at all the steps we have taken, but it is no longer in contradiction with the various propositions which are called intuitive, and which are derived from more or less elaborate empirical notions. Measurable magnitude. So far we have not spoken of the measure of magnitudes. We can tell if any one of them is greater than any other, but we cannot say that it is 2 or 3 times as large. So far I have only considered the order in which the terms are arranged, but that is not sufficient for most applications. We must learn how to compare the interval which separates any two terms. On this condition alone will the continuum become measurable, and the operations of arithmetic be applicable. This can only be done by the aid of a new and special convention, and this convention is, that in such a case the interval between the terms a and b is equal to the interval which separates c and d. For instance, we started with the integers, and between two consecutive sets we intercalated n intermediary sets. By convention we now assume these new sets to be equidistant. This is one of the ways of defining the addition of two magnitudes. For if the interval AB is by definition equal to the interval CD, the interval AD will by definition be the sum of the intervals AB and AC. This definition is very largely, but not altogether, arbitrary. It must satisfy certain conditions, the commutative and associative laws of addition, for instance, but, provided the definition we choose satisfies these laws, the choice is indifferent, and we need not state it precisely. Remarks. We are now in a position to discuss several important questions. 1. Is the creative power of the mind exhausted by the creation of the mathematical continuum? The answer is in the negative, and this is shown in a very striking manner by the work of Dupin-Raymond. We know that mathematicians distinguish between infinitesimals of different orders, and that infinitesimals of the second order are infinitely small, not only absolutely so, but also in relation to those of the first order. It is not difficult to imagine infinitesimals of fractional or even of irrational order, and here once more we find the mathematical continuum which has been dealt with in the preceding pages. Further, there are infinitesimals which are infinitely small with reference to those of the first order, and infinitely large with respect to the order 1 plus e, however small e may be. Here then are new terms intercalated in our series, and if I may be permitted to revert to the terminology used in the preceding pages, a terminology which is very convenient, although it has not been consecrated by usage, I shall say that we have created a kind of continuum of the third order. It is an easy matter to go further, but it is idle to do so, for we would only be imagining symbols without any possible application, and no one will dream of doing that. This continuum of the third order, to which we are led by the consideration of the different orders of infinitesimals, is in itself of but little use and hardly worth quoting. Geometers look on it as a mere curiosity. The mind only uses its creative faculty when experiment requires it. 2. When we are once in possession of the conception of the mathematical continuum, are we protected from contradictions analogous to those which gave it birth? No, and the following is an instance. He is a savant indeed who will not take it as evident that every curve has a tangent, and in fact if we think of a curve and a straight line as two narrow bands, we can always arrange them in such a way that they have a common part without intersecting. Suppose now that the breadth of the bands diminishes indefinitely. The common part will still remain, and in the limit, so to speak, the two lines will have a common point, although they do not intersect, that is, they will touch. The geometer who reasons in this way is only doing what we have done when we proved that two lines which intersect have a common point, and his intuition might also seem to be quite legitimate. But this is not the case. We can show that there are curves which have no tangent, if we define such a curve as an analytical continuum of the second order. No doubt some sacrifice analogous to those we have discussed above would enable us to get rid of this contradiction, but as the latter is only met with in very exceptional cases, we need not trouble to do so. Instead of endeavouring to reconcile intuition and analysis, we are content to sacrifice one of them, and as analysis must be flawless, intuition must go to the wall. The physical continuum of several dimensions. We have discussed above the physical continuum as it is derived from the immediate evidence of our senses, or, if the reader prefers, from the rough results of Fechner's experiments. I have shown that these results are summed up in the contradictory formulae A is B, B is C, and A is smaller than C. Let us now see how this notion is generalized, and how from it may be derived the concept of continuums of several dimensions. Consider any two aggregates of sensations. We can either distinguish between them, or we cannot. Just as in Fechner's experiments the weight of 10 grams could be distinguished from the weight of 12 grams, but not from the weight of 11 grams. This is all that is required to construct the continuum of several dimensions. Let us call one of these aggregates of sensation an element. It will be in a measure analogous to the point of the mathematicians, but will not be, however, the same thing. We cannot say that our element has no size, for we cannot distinguish it from its immediate neighbours, and it is thus surrounded by a kind of fog. If the astronomical comparison may be allowed, our elements would be like nebulae, whereas the mathematical points would be like stars. If this be granted, a system of elements will form a continuum if we can pass from any one of them to any other by a series of consecutive elements such that each cannot be distinguished from its predecessor. This linear series is to the line of the mathematicians what the isolated element was to the point. Before going further, I must explain what is meant by a cut. Let us consider a continuum C, and remove from it certain of its elements, which for a moment we shall regard as no longer belonging to the continuum. We shall call the aggregate of elements thus removed a cut. By means of this cut, the continuum C will be subdivided into several distinct continuums. The aggregate of elements which remain will cease to form a single continuum. There will then be on C two elements, A and B, which we must look upon as belonging to two distinct continuums, and we see that this must be so, because it will be impossible to find a linear series of consecutive elements of C, each of the elements indistinguishable from the preceding, the first being A and the last B, unless one of the elements of this series is indistinguishable from one of the elements of the cut. It may happen, on the contrary, that the cut may not be sufficient to subdivide the continuum C. To classify the physical continuums, we must first of all ascertain the nature of the cuts which must be made in order to subdivide them. If a physical continuum C may be subdivided by a cut reducing to a finite number of elements, all distinguishable the one from the other, and therefore forming neither one continuum nor several continuums, we shall call C a continuum of one dimension. If, on the contrary, C can only be subdivided by cuts which are themselves continuums, we shall say that C is of several dimensions. If the cuts are continuums of one dimension, then we shall say that C has two dimensions. If cuts of two dimensions are sufficient, we shall say that C is of three dimensions, and so on. Thus the notion of the physical continuum of several dimensions is defined, thanks to the very simple fact that two aggregates of sensations may be distinguishable or indistinguishable. The mathematical continuum of several dimensions. The conception of the mathematical continuum of n dimensions may be led up to quite naturally by a process similar to that which we discussed at the beginning of this chapter. A point of such a continuum is defined by a system of its distinct magnitudes, which we call its coordinates. The magnitudes need not always be measurable. There is, for instance, one branch of geometry independent of the measure of magnitudes, in which we are only concerned with knowing, for example, if, on a curve ABC, the point B is between the points A and C, and in which it is immaterial whether the arc AB is equal to or twice the arc BC. This branch is called analysis-citus. It contains quite a large body of doctrine which has attracted the attention of the greatest geometers, and from which are derived, one from another, a whole series of remarkable theorems. What distinguishes these theorems from those of ordinary geometry is that they are purely qualitative. They are still true if the figures are copied by an unskilful draftsman, with the result that the proportions are distorted and the straight lines replaced by lines which are more or less curved. As soon as measurement is introduced into the continuum we have just defined, the continuum becomes space, and geometry is born. But the discussion of this is reserved for Part 2. End of Chapter 2.